Welcome to the Donaldson Clean Solutions webinar, Buying Diesel Fuel Beyond Price. I am Jim Doyle, Senior Engineer at Donaldson. This is our fourth webinar on fuel and fuel handling practices. The others are posted at mycleandiesel.com and on YouTube. This webinar will run approximately 20 minutes. Henry Ford said, "If you always do what you've always done, you'll always get what you've always got." This from a man who learned from his own experience producing black Model Ts from 1908 to 1927 that not keeping up with industry changes and taking a year and a half off to retool for the Model A would cost him about 50% of his company's share of the automobile market. Most everyone here today buys or uses diesel fuel routinely. Over the last few years, it has become more routine to have unpredictable experiences using diesel fuel in modern equipment. This is because engine technology, fuel filtration needs, and even the fuel itself have changed significantly. For the most part, fuel purchasing and handling behaviors and many critical diesel fuel standards have remained relatively constant through all of that technology advancement. The objectives for today are to describe the change in diesel fuel engines, describe diesel fuel and diesel standards and how they relate to modern engine use, describe critical aspects in diesel fuel properties, and finally, purchasing and handling practices to limit issues for users. So what has changed? A wide range of on-equipment and fuel technologies have evolved rapidly to meet emissions requirements over the last 10 years or so. Selective catalytic reduction, or SCR, exhaust gas recirculation, or EGR, diesel exhaust fluid, or DEF, for NOx reduction, and high-pressure common rail injection systems are now used for as complete a combustion of hydrocarbons as possible. There are also new engine oil formulations and diesel particulate filters for managing soot particulate emissions. Lower viscosity oils are now common to reduce drag in engines, and engine drivetrain electronics to better manage emissions and system efficiency. And improved aerodynamics are all involved in increasing fuel economy. Diesel fuel itself has also changed at the same time. Sulfur is now essentially gone from diesel, and ultra-low sulfur is the norm. Sulfur, which has many useful functions in fuel, has dropped from 15,000 ppm to 15 ppm or less in essentially all diesel fuel. The method of refining and the functional additive chemistry have also changed. Biodiesel is now commonplace. It is essentially unavoidable and is present in most fuel supplies at some point over the course of a year. All of that change has made engines much more complex, but most of it goes unnoticed to the operator. The change to high-pressure common rail fuel systems has brought forth one of the most significant issues contributing to unplanned downtime, and that is unpredictable fuel filter plugging. Shown here in red on the chart is a line depicting the cumulative number and size of particles in diesel fuel. Diesel fuel, being a very thin fluid, does not contain large particulate that you can see, something above about 40 microns. In fact, as you can see, there are very few particles above about 6 microns. Overlaid on that information is a set of curves depicting traditional diesel fuel engine filtration needs over the last 30 years or so. The green line shows the performance of 25 micron filters common on very old equipment. Not surprisingly, it is not very good at removing small particulate and basically lets it all through. The light blue line shows 15 micron filtration for equipment roughly 15 to 20 years old. The dark blue line is 7 micron filtration for equipment 5 to 15 years old. And the purple line way at the top shows the filtration performance needed to remove nearly all particulate as small as 2 microns to protect modern high-pressure common rail fuel systems. The two most important things to note here are that older equipment is not sensitive to particulate below 7 micron or so, and 95% of fuel particulate is below 6 microns in size. This is the reason fuel filters plug so unpredictably today for high-pressure common rail engines. The secondary fuel filters now have a much larger job to do, and the dirtier the fuel, the faster modern filters plug because they now have to stop everything. There are many standards that define and characterize diesel fuel properties and ways to evaluate fuel. ASTM D975 and the European EN 590 are the most common, widely recognized, overarching standard sets. ASTM D6751 and its European counterpart EN 14214 are the common standards for 100% biodiesel product. Diesel fuel is not a single thing. It is a mixture of many chemicals that, when run through the various ASTM and other standards, produce results within the defined ranges. Obviously, hydrocarbons from petroleum products are the major portion, but there are many other things added to meet all the standards. There are a few, if any, raw fuel sources out of a refinery that meet all the standards without other additives being blended in for various reasons. This is a quick outline of what fuel is actually made of. A typical tanker contains 7,500 gallons of fuel, and that comes along with some biodiesel, a gallon or two of mainly dissolved water, about a gallon of glycerin, which is a byproduct of the biodiesel manufacturing process, 5 to 40 gallons of various fuel additives, and a tiny amount of dirt in the fuel if the fuel has been clean and dry and seen well-maintained infrastructure up to the time of delivery. Just where are all these additions made to the fuel? Most fuel purchased by end users through the normal channels meets the minimum needs for modern equipment, but it is important to be aware of what is being added from the time of manufacture through distribution and at the end user to understand how that can impact operation and performance. Additives are put in at various points in distribution, and it's not the same everywhere. The US, Canada, and Europe dose additives at different places in distribution, but we will attempt to cover these as generically as possible here. At the refinery, refined hydrocarbons are chosen to blend into ultra-low sulfur diesel, and some or all of the additive package can be put into the fuel at that time. Corrosion inhibitor, cetane improver, and stability improver are typically added at the refinery, as these are needed to prevent infrastructure damage in pipeline transport or other distribution. They also perform the same functions to help meet industry standards for the end user customer's equipment. Fuel at this point is suitable for transport through pipelines in the U.S. If fuel is being picked up directly at the refinery, it may receive a more extensive additive package so it meets all minimum standards. Typically, conductivity improver, cold flow improver, and lubricity improver are added downstream from manufacture at the terminal level. Biodiesel is now blended into fuel per regulatory requirements and more generally is a lubricity additive. Some U.S. states, Canada, and Europe mandate blending it in at various levels over the course of the year. There are now very few exemptions for its use in publicly available fuel supplies. Biodiesel is also registered with the EPA as a lubricity improver. It can be blended up to 5% without being identified as a biodiesel blended fuel. If available to a fuel manufacturer, it is a more cost-effective lubricity improver and is therefore used widely when available. Biodiesel blending of 5% and higher is generally done at the terminal while filling the tanker truck or potentially on the end user site if a customer is using an unusually high percentage. Premium fuel additives are often added at distribution terminals as well. These are mainly detergent additives recommended for high-pressure common rail fuel systems. Additionally, some customers ask for more stability improver to prevent fuel oxidation in storage for backup gensets or seasonal use. Fuel stability decreases significantly with the blending of biofuels, so this is more of a common concern now than it has been in the past. At this point, it is worth covering seasonal blending strategies, as this is a major contributor to operability and filterability of fuel. The ASTM D975 diesel standard provides guidance on fuel blending and cloud point needs for different regions. The colder the region, the lower the natural cloud point recommendations, and people will add cold flow improver as well to adjust this. The cloud point of a fuel is the point at which a portion of the hydrocarbon mixture begins to form solids, gels, or wax. Changing cloud point naturally by blending lower cloud point fuel into higher cloud point fuel, or blending number 1 into number 2, is the only way to ensure fuel actually stays liquid at a lower temperature as compared to adding cold flow improver. Cold flow improver can change the test result for the cold filter plugging point and assist in certain cold weather starting situations, but it does not allow for lower temperature operation or at which temperature the fuel begins to gel. We have a 20-minute video presentation on cold weather and diesel already posted on MyCleanDiesel if you wish to dig further into this topic. At end-user customers, various packages of additive are blended as well. Many customers add customized additive packages on site for their particular needs. There are additional cetane boosters, lubricity improvers, premium detergents, stabilizers, and cold flow improvers added. Water management additives are also applied at the end user. They include emulsifiers and demulsifiers. They are both put in to manage water, but function very differently. Emulsifiers are added to allow the fuel to carry more water and keep it from building up in tanks and infrastructure. Demulsifiers are added to force water out of fuel and improve fuel-water separator performance. We also have a 20-minute video presentation on water management on mycleandiesel.com if you have greater interest in this area. What does this mean to an end user? Do you know what is in the fuel you are getting? The reality in the U.S. is that fuel in pipelines is considered fungible, meaning it could be put in by one manufacturer and removed at the other end by someone else's fuel. It is like depositing cash in a bank. You don't get the same dollar bills back when you go and withdraw money. The additive package put in at the manufacturer is therefore somewhat of an unknown at the other end. Recall that only a portion of the additive package is put in as the fuel is put down the pipeline, and more is added at the distribution terminal. Do you know the values and properties of the fuel you buy and how they have been adjusted? Do you know what the properties need to be improved for your use? So what does this mean to an end user? These are good things to keep in mind when adding more at time of purchase. More is not always better, and how you dose additive can be critical to it being effective in the fuel. Probably the most common occurrence of this type of issue would be the use of cold flow improver. It actually functions opposite of how most people assume it does. It needs to be put in when the fuel is warm, typically between 45 and 50 degrees Fahrenheit, and at the lowest concentration recommended to be the most effective. Adding more cold flow improver to cold fuel or to fuel with the correct dose already in it will decrease the fuel's cold weather functionality and plug filtration above the cloud point. Another concern is the technique used to dose additive at distribution or at customer sites. Certain portions of additive packages have maximum concentrations that should not be exceeded in the fuel, or they can generate significant particulate. An additive package designed for continuous injection in a pipeline may be very concentrated, but if this same package is splash blended, also known as dumped in, at a high concentration, it may never fully disperse in the fuel and wind up in the filters or at the bottom of the tank as a waste of money. Additive packages designed for splash blending will typically have a lower concentration to avoid these types of issues. Some components of the additive package do tend to deplete in distribution, including corrosion inhibitor and lubricity improver. These additives are designed to coat surfaces to protect things and can react with other materials in the fuel supply to generate fine particulate that may settle in tanks, rapidly plug fine filters, or form injector deposits. Regardless of their effect, certain additive components that have done their job or reacted with other chemistries will no longer perform that function and may need to be replenished at the end user. So considering all of this information, what does the typical fuel cert tell me? Diesel fuel certs supplied to end users tend to have a pretty typical set of parameters called out that people pay attention to. Cetane is describing the combustion behavior of the fuel, and the higher the cetane number correlates to better diesel fuel combustion and ignition properties. Heating value in BTUs describes the energy content of the fuel. Number 2 diesel having a higher energy content than number 1. This is one key factor in selecting fuel for winter filterability and equipment operability. Cloud point is the temperature at which the fuel generates enough solids to become cloudy. In the photo, you can see number 1 off-road diesel fuel in winter above its cloud point, and on the left, number 2 off-road and on-road on the right below their cloud point. This is a key factor in determining winter filterability. Cold filter plugging point is the temperature at which the fuel fails the cold filter plugging point test. It is generally a little below the cloud point and can be much lower than the cloud point of fuels containing cold flow improver. This can be somewhat misleading because equipment filters and dispenser filters have become much more efficient and plug much quicker than in the past. Lubricity, reported as a wear scar test result, indicating the fuel's ability to prevent mechanical wear on moving parts. Stability describes the thermal stability of a fuel and may relate to acceptable storage time. There are a range of tests to assess this fuel parameter, and it can be critical for fuel when it will be in storage for extended periods of time. It should be checked at the time of purchase and as the fuel sits in storage to monitor change. Clear and bright may be called out on the fuel cert. This is a common industry term traditionally used to say fuel is fit for use. This may have been the case long ago, but modern engine needs have advanced to the point that this is irrelevant. Fuel that looks clear and bright can be full of particulate that is harmful to engines. Just a small amount of fuel from these samples was pulled through the filter patches in the center, and the high debris load in the fuel is quite obvious. Water and sediment is another test on bulk fuel, describing the amount of solids and or water in the sample. It is not intended to correlate to modern needs of fuel cleanliness post-secondary fuel filters on new equipment. The limits of detection and reporting for this test are not adequate to predict fuel usability in new equipment. This standard was developed long ago for older engines and bulk fuel transfer, not final product for use in newer equipment. Hopefully more detail than clear and bright or a water and sediment result is provided. Water content in ppm, describing total water, may be more effective. This can include free, emulsified, and dissolved water. Good quality fuel should have only dissolved water and should be below 150 to 200 ppm. If it is higher than 100 to 150 ppm at the time of receipt, the fuel has likely picked up some water in distribution. For particulate, a much more relevant ISO particle count is beginning to show up, describing the concentration and distribution of particulate 4 microns and larger at very low levels. You will see numbers like 18, 16, 13 as a maximum for modern systems, which is roughly 1 milligram per liter of particulate. This type of particulate load characterization has been common in oil cleanliness measurements and is now working its way into the fuel purchase specifications and certifications. It is worth pointing out that this maximum level is still 64 times dirtier than high-pressure common rail injector systems can tolerate, so significant filtration still needs to be done prior to the injection system. Corrosion, fuel corrosivity, is literally measured by rusting metals in the lab with fuel. It is a measure of the likelihood of a fuel in controlled conditions to rust infrastructure or engine parts. Biodiesel content, typically reported as a percentage as B5 or 5%, B10 or 10%, etc., is also called out on many fuel certs. What does the fuel cert not tell me? All of that data can be meaningful, but does any of it give you a complete picture of what the fuel will act like for your use? It's a lot like looking at a list of ingredients and trying to figure out if something will taste good. It might not. It does tell you that the fuel meets the required specifications on the certification. A major set of factors that need to be considered together are heat content, number 1 and number 2 blend, cloud point, and CFPP for winter operation. Only hinted at in the listed information on the cert is the balance of number 2 for high heat content and number 1 for good cold weather properties but having a lower heat content. It also doesn't specifically call out the impact of cold flow improver. Cold flow improver was developed in the 1960s to allow gelled fuel to be pumped through pipes, pumps, and screens. Gelled fuel will not pass through filters fine enough to remove the hard particulate that is in fuel and will harm the engine. Traditionally, this has been dealt with by using only very coarse filters in winter, which do not impact actual fuel cleanliness. The cert may not tell you that you have bio in your fuel. If it is below 5%, it will not be called out, and this can contribute to shorter stable fuel storage life. A higher percentage to meet a government mandate or customer requirement should be noted as a B5, a B10, B20 blend. A final point on biodiesel is that the certification that is typically provided for a B100 fuel source is generally not for the specific batch you have received. Biodiesel plant production is usually certified on a less frequent basis due to the high cost of fuel properties testing. If an ISO cleanliness code is not given on your cert, it is not possible to assess if the fuel is in compliance with equipment manufacturer cleanliness requirements and filtration to meet that maximum or possibly significantly cleaner target would be good insurance. Depending on where in the distribution path fuel certification testing was run, it may not reflect all of the additives in the fuel at end-user customer sites. This is a lot of information to digest regarding fuel and fuel properties, and it is not realistic to keep it all in mind until you need it. Probably the best overall technical resource for diesel fuel information is the Chevron Diesel Fuels Technical Review. It is linked at mycleandiesel.com in the technical section and is also searchable on the internet. Thank you for your time viewing this webinar. Our next session is planned for October 22nd and 23rd, 2015. Please watch for notification from mycleandiesel.com.